Looking at this industry snapshot of Fortune 100 companies, you see a perfect 10 out of 10 adoption rate across sectors like manufacturing and insurance. These are environments where a single system failure means grounded supply chains or halted financial clearing. This flow diagram maps out where Kafka actually sits. It acts as the central nervous system, taking massive influxes of data from application logs and web servers and continuously feeding that data into downstream batch processors and analytics engines. Modern data pipelines operate under extreme performance requirements. Systems routinely demand processing capabilities that exceed 1 million transactions per second, requiring milliseconds of latency between the moment an event is generated and when it becomes available for processing. Traditional message queues struggle to hit these numbers because of a structural paradox. Older designs force the message broker to act as an active manager, constantly tracking exactly which consumer has read which message, acknowledging receipts, and deleting read data. At scale, maintaining all that state information consumes immense computing power, and the server chokes. Kafka achieves its massive scale by flipping this relationship. It relies on dumb brokers and smart consumers. The system strictly separates the logical intent of the data from its physical storage, stripping the server of almost all active management duties. To understand Kafka, you have to stop thinking about it as a manager of messages. It is an immutable, distributed log. It writes data to disk and leaves it there. We begin with the topic. This is Kafka's basic logical unit. When an application generates data, like a stream of user clicks, it targets a specific topic name. It's simply a category. If that logical topic maps directly to a single physical file on a single server, you hit a hard hardware ceiling. Throughput is limited by the capacity of one spinning disk. Push 1 million events per second into it, and the pipe bursts under the pressure. To bypass this physical bottleneck, we need to construct a 4-layer architecture. We will separate the logical topic from its storage, wrap that in a service layer, and govern the whole thing with coordination. Horizontal scaling cannot happen as long as the logical concept of a data stream is shackled to a single piece of hardware. We solve the storage bottleneck with the partition. The partition is the actual physical realization of the logical topic. In source image 6, the logical topic divides into partitions 0, 1, and 2. The incoming stream is sharded across these independent sublogs. They are sequential, append-only structures, where each message receives an offset, a unique, permanently incrementing ID serving as its exact address. Because these partitions act as independent logs, multiple producers can write to them simultaneously without locking each other out. By sharding a single topic into multiple partitions, the maximum throughput is no longer dictated by one drive's write speed. It scales up to the aggregate I/O capacity of the entire server cluster. But creating high-throughput storage introduces a new problem on the receiving end. With 10 partitions receiving thousands of messages a second, a single consumer application trying to process all that data will instantly become a bottleneck. We scale the pull side of the equation using the consumer group mechanism. Instead of one application reading the stream, you deploy a cluster of instances working together as a team. Strict rule governs this mechanism. A specific partition can only be consumed by exactly one member of a consumer group at any given time. This guarantees that 2 instances in the same group never process the exact same message, preventing duplicate work. If entirely different business units need that exact same data stream, they simply deploy their own separate consumer groups. This is the broadcast model. The separate groups read the identical log entirely independently without interfering with one another. On the right of this schematic, Group 1 actively reads the topic, balancing the load across Consumer 1 and 2.
Crucially, the broker isn't tracking them. The consumer group stores its own offset pointer, updating its address in the log after finishing a batch. By making the consumer responsible for tracking its own position, the broker remains stateless. It just serves files from disk, keeping resource overhead incredibly low. Now we must account for hardware mortality. Servers will eventually crash. If a machine holding your partitions dies and that data vanishes, the entire system design is useless. This introduces the service layer. The physical server node that acts as the container for these partitions is called a broker. To prevent data loss, Kafka relies on a replication factor. Every partition is copied multiple times and distributed across different brokers in the network. In this cluster map, green topic partition 0 is the leader on broker 2, actively handling all read and write requests.
On broker 0, it acts as a follower, an entirely passive node that silently synchronizes data from the leader to act as a hot standby. The system monitors which followers are actually keeping pace with the leader, organizing them into an in-sync replica list, or ISR. This active-passive replication model guarantees high availability. A broker can suffer a catastrophic failure, and data continues to flow seamlessly from the surviving replicas. With data scattered across hundreds of brokers and thousands of partitions, the cluster requires a brain. Who decides which node becomes a leader, and how does the network instantly agree when a failure occurs? The coordination layer handles this. In traditional Kafka deployments, an external system called Zookeeper monitors broker health and stores the metadata for the entire cluster. Upon startup, the brokers race to register with Zookeeper. The first one to succeed is elected the controller, assuming responsibility for cluster-wide decisions. If a broker's network cable is cut, Zookeeper detects the connection timeout and immediately alerts the controller that a node has died. The controller intervenes instantly. It checks the in-sync replica list for the affected partitions, promotes healthy followers to be the new leaders, and signals the brokers to update their routing. Centralizing authority prevents split-brain scenarios, where a network glitch tricks two nodes into believing they are both the active leader for the same partition. Offloading consensus to Zookeeper and the controller provides a single source of truth, keeping the distributed network stable no matter how chaotic the environment gets. We started with a single logical concept, a topic, and deconstructed it into a massive, distributed, fault-tolerant cluster. Returning to this end-to-end schematic, the full pipeline is visible. A producer pushes data in, the cluster routes it to the correct partition leaders, and the consumer group pulls it out based on its own tracked offsets. This efficiency is the result of strict separation across 4 layers. The logical topic categorizes the data, the storage partitions divide the data, the service brokers host the files, the coordination controller governs the rules. Achieving this scale requires a specific trade-off. By treating data strictly as an append-only log, Kafka sacrifices global message ordering and complex routing capabilities to gain immense durability and raw throughput. Because partitions operate independently, strict sequential order is only guaranteed within a specific partition. If an application requires chronological exactness across millions of events, the developer must ensure those related events are routed to the identical partition.
For an engineer designing systems today, knowing how to type a Kafka command is less important than understanding why the system was structured this way in the first place. Traditional messaging failed because it coupled intent with execution. Kafka scales because it severs that link. Decoupling the logical meaning of your data from the physical reality of how it is stored is the absolute requirement for surviving internet-scale traffic.